Let's talk about regression analysis, very popular topic in data science and statistics. So all it is trying to fit a curve, some sort of a function, to a set of observations, and then you can use that function to predict new values that you haven't seen yet. That's all there is to it. So let's start off by talking about the simplest form of regression analysis, linear regression. Let's talk about linear regression. You hear a lot about regression analysis in the field of data science. Sounds fancy, but it's actually a very simple concept. Let's see. So linear regression, all it is fitting a straight line to a set of observations. That's it. That's all there is to it. So for example, let's say that I have a bunch of people that I measured, and the two features that I measured of these people are their weight and their height. So I'm showing the weight on the x-axis and the height on the y-axis. And I can plot all these data points of people's weight versus their height, and I can see, that looks like a linear relationship, doesn't it? Maybe I can fit a straight line to it and use that to predict new values. And that's what linear regression does. So in this example, I might end up with a slope of 0.6 and a y-intercept of 130.2 in this example, and that defines a straight line, given a slope and a y-intercept, that fits the data that I have best. And I can use that line to predict new values. So you can see that the weights that I observed only went up to people that weighed 100 kilograms. But what if I had someone who weighed 120 kilograms? Well, I could use that line to then figure out where would the height be for someone with 120 kilograms based on all this previous data. That's it. I don't know why they call it regression. Regression kind of implies that you're doing something backwards. And I guess you can think of it in terms of you're creating a line to predict new values based on observations you made in the past, backwards in time, but it seems like a little bit of a stretch. It's just a confusing term, quite honestly, and yet another way that we kind of obscure what we do with very simple concepts using very fancy terminology. So don't let linear regression trip you up in terms of sounding fancy. All it is fitting a straight line to a set of data points. How does it work? Well, internally it uses a technique called least squares, ordinary least squares. It's also known as OLS. You might see that term tossed around as well. And the way it works is it tries to minimize the squared error between each point and the line. And the error is just the distance between each point and the line that you have. So if we sum up all the squares of those errors, sounds a lot like when we computed variance, right? Except instead of relative to the mean as to this line that we're defining, we can measure the variance of the data points from that line. And by minimizing that variance, we can find the line that fits it the best. Now, you'll never have to actually do this yourself the hard way, but if you had to for some reason, or if you're just curious about what happens under the hood, this describes the overall algorithm here for you of how you would actually go about computing the slope and y-intercept yourself the hard way if you needed to. It's really not that complicated. The slope just turns out to be the correlation between the two variables times the standard deviation in y divided by the standard deviation in x. And it might seem a little bit weird that standard deviation just kind of creeps into the math naturally there, but remember correlation had standard deviation baked into it as well, so it's not too surprising we have to reintroduce that term. The intercept can then be computed as the mean of the y minus the slope times the mean of x. And again, even though that's really not that difficult, Python will do it all for you. But the point is that these aren't complicated things to run. They can actually be done pretty efficiently. So again, just remember least squares minimizes the sum of squared errors from each point to the line. And another way of thinking about linear regression is that you're defining a line that represents the maximum likelihood of an observation lying there, the maximum probability of the y value being something for a given x value. So again, people sometimes call this maximum likelihood estimation, and it's just another example of people giving a fancy name to something that's very simple. So if you hear someone talk about maximum likelihood estimation, they're really talking about regression. They're just trying to sound really smart. But now you know that term too, so you too can sound smart. There is more than one way to do it. We talked about ordinary least squares as being a simple way of fitting a line to a set of data, but there are other techniques as well, gradient descent being one of them. And it works best in three-dimensional data, so it kind of tries to follow the contours of the data for you. It's very fancy and obviously a little bit more computationally expensive, but Python does make it easy for you to try it out if you want to compare it to ordinary least squares. Usually, though, least squares is a perfectly good choice for doing linear regression, and it's always a legitimate thing to do. But if you do run into gradient descent, you will know that that is just an alternate way of doing linear regression, and it's usually seen in higher dimensional data. So how do I know how good my regression is? How well does my line fit my data? Well, that's where R squared comes in. And R squared is also known as the coefficient of determination. Again, someone trying to sound smart might call it that. But usually it's called R squared. It is the fraction of the total variation in Y that is captured by your model. So how well does your line follow that variation that's happening? Are we getting an equal amount of variance on either side of your line or not? That's what R squared is measuring. And to actually compute the value, you take 1 minus the sum of the squared errors over the sum of the squared variations from the mean. So it's not very difficult to compute. But again, Python will give you functions that will just compute that for you, so you'll never have to actually do that math yourself. The way to interpret R squared, you'll get a value that ranges from 0 to 1. 0 means your fit is terrible. It doesn't capture any of the variance in your data. And 1 is a perfect fit. So all of the variance in your data gets captured by this line. So all the variance you see on either side of your line should be the same in that case. So 0 is bad, 1 is good. That's all you really need to know. Something in between is something in between. So a low R squared value means it's a poor fit. High R squared value means it's a good fit. And as you'll see in the coming lectures, there's more than one way to do regression. Linear regression is one of them. It's a very simple technique, but there are other techniques as well. And you can use R squared as a quantitative measure of how good a given regression is to a set of data points, and then use that to choose the model that best fits your data. Okay? So let's play with it and actually compute some linear regression in R squared. Let's have some fun with linear regression hands-on. So go ahead and open up the linear regression IPython notebook file and follow along with me if you will, because I do want you to play around with this to get a good feel of it. So we'll start by creating a little bit of Python code here that generates some random-ish data that is in fact linearly correlated. So in this example, I'm going to fake some data about page rendering speeds and how much people purchase, just like a previous example. So we're going to fabricate a linear relationship between the amount of time it takes for a website to load and the amount of money people spend on that website. So all I've done here is I've made a normal distribution of page speeds centered around 3 seconds with a standard deviation of 1 second, and I've made the purchase amount a linear function of that. So I'm making it 100 minus the page speeds plus some normal random distribution around it times 3. And if we scatter that, we can see that the data ends up looking like this. Okay, so you can see just by eyeballing it that there's definitely a linear relationship going on there, and that's because we did hard code a real linear relationship in our source data. So let's see if we can tease that out and find the best fit line using ordinary least squares. Now, we talked about how to do ordinary least squares in linear regression in the slides, but you don't have to do any of that math yourself because the SciPy package has a stats package that you can import. So you can say from SciPy import stats, and then you can just call stats.linregress on your two features. So I have a list of page speeds and a corresponding list of purchase amounts. Linregress will give me back a bunch of stuff. So it gives me back all of these variables that I'm getting back, the slope, the intercept, and this is what I need to actually define my best fit line. It also gives me the R value from which we can get R squared and measure the quality of that fit, and a couple of things that we'll talk about later in the course. For now, we just need slope, intercept, and R value. So let's go ahead and run these. So there's my line, and let's go ahead and find the linear regression best fit. Now the R squared value of the line that we got back is 0.99. That's almost 1.0. So that means we have a really good fit, which isn't too surprising because we made sure there was a real linear relationship between this data. Even though there is some variance around that line, our line captures that variance. So we have roughly the same amount of variance on either side of the line, which is a good thing. It tells us that we do have a linear relationship and our model is a good fit for the data that we have. Let's actually plot that line. So this little bit of code will actually create a function to draw that red best fit line alongside the data. So a little bit more of matplotlib magic here. We're going to make a fit line list, and we're going to use this predict function we wrote to take the page speeds, which is our x-axis, and create the y function from that. So instead of taking the observations for amounts spent, we're going to find the predicted ones just using the slope times x plus the intercept that we got back from the linregress call above. So basically we're going to do a scatter plot like we did before to show the raw data points, the observations, And then we're also going to call plot on that same pyplot instance using our fit line that we created, using the line equation that we got back, and show them all both together. Do that, and it looks like that. So you can see that our line is in fact a great fit for our data. It goes right smack down the middle. And all you need to predict new values is this predict function. So given a new, previously unseen page speed, we could predict the amount spent just using the slope times the page speed plus the intercept. That's all there is to it. So, time to get your hands dirty. Try increasing the random variation in the test data and see if that has any impact. Remember, the R-squared is a measure of the fit. How much do we capture the variance? So the amount of variance, well, see if it actually makes a difference or not. That's linear regression. Pretty simple concept. All we're doing is fitting a straight line to a set of observations, and then we can use that line to make predictions of new values. That's all there is to it. But why limit yourself to a line? There's other types of regression we can do that are more complex, so we'll do that next.